Earlier we talked about stabilization of the origin of an LTI system through state feedback. Okay, and in this lecture we will generalize that, or we will extend that method to the case where we use output feedback, okay, to stabilize the system. Okay, so let's first put down the problem definition. So this is the system which we want to stabilize. Okay, y equals cx plus du. So we want to figure out some input signal so that when we drive the system with that control input, all the solutions or the state solution x of t converges to the origin. And what we have in our disposal is the measurement coming from the system. Therefore, measured or known are the signals y of t, and also since it's us who's applying to the system the control input u of t is also known. Okay, and what we want is we want to figure out a control input u of t based on the output information y of t, so that x of t converges to the origin. Okay. Now, to be able to solve this problem or achieve this goal, the minimal set of assumptions turns out to be that we have to assume that the pair AB is controllable, or the system is, stabilizable, and also we require that the system is also detectable. Okay. Suppose that AB stabilizable and the pair CA is detectable. If either of these conditions is missing, then we cannot achieve this goal. We cannot stabilize the origin by output feedback. Okay, now here is the first thing that comes to mind. Apply state feedback u of t equals minus k x of t, and k is a properly chosen feedback law, and by properly chosen I mean the matrix A minus bk, can be called the closed loop system matrix, is exponentially stable. Okay, and in fact we did that, and we can choose in our previous lectures, and we can choose such a k because the pair is stabilizable. Okay. Now the problem with this solution suggestion is that we don't have direct access to the entire set of state variables. Okay, we have only a partial information regarding the state, and that information is the output y of t. Okay, so that's the problem related to this solution candidate. Therefore, it's not actually an applicable solution, directly applicable solution. So the problem is we do not have access to the entire state information x of t. Now what we have to do is we have to somehow come up with a new solution, or perhaps revise this solution candidate. And one nice way to revise it is as follows: revised solution. Now, in our previous lecture, we saw that if a system is detectable, then we can construct an observer which is running within our computer, and that observer uses only this pair of signals, okay, as its input, and then that observer produces an estimate of the state x hat of t, and that estimate becomes better and better as time goes on. So since we don't have direct access to x of t, perhaps we can construct an observer. That observer produces an estimate of the state x hat of t, and instead of driving the system with u equals minus k x of t, because we cannot do that, we drive it with minus k x hat of t. Instead of x, we use the estimate of this state, okay? So it looks like a nice suggestion, but it's not directly obvious that it would work, okay? Because we're making some intuitive steps, and sometimes such steps may turn out to be in the wrong direction. But in this case, it will be in the right direction. Okay, so here is the revised solution. Construct an observer first. Okay, which produces the estimate, which we call x hat. X hat dot equals a x hat plus bu, and u is the control signal, the same control signal that you're using to drive the actual system. Plus, to that dynamics, you add a correction term, okay? Plus L times y minus y hat. And y hat is cx hat plus du. And we choose the observer gain L such that the matrix A minus LC is exponentially stable. Okay, and we know that we can choose such an L. We showed using the Lyapunov test for detectability, because the system is detectable. Okay, so construct this observer that's running in our computer, and it produces the estimate x hat, and we take that information, that estimate, and run or construct our control signal with that estimate instead of the actual state. Okay, so then let u of t equals minus k x hat of t. Okay, now the problem with the first suggestion was that it was not feasible because we didn't have direct access to x of t. As far as the revised solution is concerned, there is no feasibility problem, because there's nothing that prevents us from constructing this observer or choosing L such that A minus LC is exponentially stable. Okay, and then once we have x hat, we can clearly apply, we can use that x hat in our control signal construction. Okay, now this is a feasible solution, but still we have to show that it satisfies or it produces this desired result, that is, the solution x of t converges to 0. Okay, now let's try to answer the following question: why does this solution work? Okay, so let's concentrate on the observer dynamics first, and then using the observer dynamics, let's obtain the aerodynamics, and then use the aerodynamics to figure out a representation of the overall closed loop system, where the state is of dimension 2 times the order of the original system. Okay, so as before, we stick to the notation, E being x hat minus x. So this is our error signal, and it's the difference between the estimate state and the actual state. Okay, and we have shown in the previous hour that the dynamics of the error are driven by the A minus LC matrix. Okay, so E that equals A minus LC E. So this is our equation 1. And L is chosen, the observer gain is chosen, so that A minus LC is exponentially stable. Therefore, this equation 1 tells us that the dynamics E, they're converging to, or the error is converging to 0 exponentially. Now, how about the dynamics of the actual system under the control signal U equals minus K times X hat T. So X dot equals AX plus BU, and U is minus K times X hat. X hat is the estimate that we collect from the computer in which our observer runs. U equals minus K X hat. Now that produces the following: X dot equals AX minus BK X hat, okay, and that's AX minus BK. Now let's write X hat in terms of X and E, which we can because by definition this is error, therefore X hat equals X plus error. Okay, so we have E plus X. And that reads A minus BK times X minus BK times the error signal. Okay, so let's call this dynamics 2. So error depends only on its own initial condition, but the dynamics of the actual state depends both on its own initial condition and the error initial condition, or equivalently the initial condition of the observer state X hat. Okay. Now now it's more or less, at least intuitively, it's clear that, or the intuition suggests that since E of t is converging to 0, and this is dynamics of X dot, okay, the actual state. This term here in the dynamics of X dot, this term is converging to 0 exponentially fast, okay, because of the dynamics 1, the observer error dynamics. Now, if this term is converging to 0 as time goes on, so after a while, we can more or less suppose that X dot approximately equals this, okay? We can sort of ignore that term because error is converging to 0 exponentially fast. And when we do that, this system we know must converge to the origin, the state of that system, because we have chosen the feedback gain K such that this matrix A minus BK is exponentially stable. And we were able to choose such a K because the pair AB was stabilizable. Okay, so that's the intuitive explanation why this suggestion would work, but still it's not a really rigorous explanation, so let's make it more formal and convincing. For that, what we do is we're going to put the dynamics, we're going to combine the dynamics 1 and 2 into a single big state equation. Okay, 1 and 2 implies the following. So we have X dot E dot equals this big A matrix, and this is our big X vector, you can call it, times XE. Okay. Now, okay, so X is in Rn. Okay, so X is in Rn, so n is the order of our system. The order of our observer must be the same because we're using the same dynamics, or more or less the same dynamics. And as a result, since error is X hat minus X, the error also belongs to Rn. So if we consider this thing as our new state, the first part is in Rn, the second part is also in Rn, so the entire state, the new big state, is in space R2n. Okay, so that makes this matrix 2n by 2n matrix. Okay, now let's call this vector x big, okay, and let's call this matrix A big. And now let's figure out the block entries of this big A matrix. And by looking at those block entries, we will be able to figure out the behavior of the solution of the actual system, x of t. Okay, so what's x dot? X dot is here, something times x. So that's something, we put it here, a minus bk, plus something times e, and that's something, we put it here. Okay, minus bk. And how about E dynamics, aerodynamics? E that equals, it only depends on E, therefore E that equals 0 times x plus this times E. So we put that here, A minus LC. And this is the big matrix. And once the coupled dynamics are written in this single LTI system form, it becomes obvious why this solution will work. Okay, so let's therefore conclude our analysis by looking at that LTI system. Okay, so what we have obtained is the following: x big dot equals a big times x big. Okay, and this system is of order 2n. That is twice the order of the actual plant, x dot equals ax plus bu system. Okay, now one nice thing about this new large A matrix is its upper block triangular. Okay, therefore the eigenvalues of that matrix are determined by the eigenvalues of the matrices that appear on the diagonal. Okay, so A big is upper block triangular. Okay, therefore eigenvalues of A big, okay, the big A matrix equals the union of eigenvalues of the first block and the eigenvalues of the second block, which is the matrix A minus LC. Now, what do we know about the eigenvalues of the first block, A minus bk? Now, we have chosen our feedback gain so that A minus bk is exponentially stable, therefore the eigenvalues are all with negative real parts. And we did the same thing when choosing L, our observer gain. We chose L such that A minus LC is with eigenvalues with strict negative real parts. Okay, so here we have all the real parts strictly negative, and here we have all the real parts again strictly negative. Okay, as a result, all the eigenvalues of A big are on the open left half plane, and that means our 2n by 2n matrix is exponentially stable. So that means its state x big of t must converge to 0 as time goes to infinity. And x big converging to 0 means that its components must also be converging to 0, and one of its components is the state of the plant, the actual system. Therefore, x big converging to 0 implies x of t converging to 0, and that was what we were after. We want to stabilize the origin of the plant. Okay, so this time, therefore, our intuition did work in the right direction. X big of t converges to 0 exponentially fast. All its components converge to 0 exponentially fast, and one of its components is x of t. And the stabilization is achieved. Okay, so that's how you stabilize the origin of a system, provided that it's both stabilizable and detectable. Okay, now in the second half of our lecture, we will briefly talk about the relation between a realization of a transfer function, the order of that realization, and the controllability, observability properties of the realization. Okay. Minimal realization. So suppose we start with a given transfer function, g of s. Given transfer function, g of s, and we know that for the general case where we have multi-inputs and multi-output system, okay, that transfer function in general is a matrix, okay, called g of s. For this transfer function, suppose that we obtain a realization, okay? That is a state space representation that would produce, when the relation between its input and output is considered, that would produce this given transfer function g of s, okay? So x that equals ax plus bu, y equals cx plus du. Okay, x is in Rn, y is in Rm, and the input is a vector of size k. Okay? Okay. So in this case, for instance, g of s will be what? An m by k matrix. Okay, so this state space representation is said to be a realization of g of s if, we already talked about that, if the relation between the system parameters a, b, c, d and the transfer function matrix g of s is such that c si minus a inverse b plus d produces the transfer function that's given. Okay. Now, right, so when for a given transfer function we obtain these four parameters a, b, c, and d, the order of the system n is said to be the order of the realization. Okay, now the number n is the order of the realization. Okay, and a realization is said to be minimal, okay, for a given transfer function. Certain minimization is said to be minimal if you cannot find another minimization with an order that's strictly less than the order of that realization. Okay, now a realization of g of s is said to be minimal if there is no realization of the same transfer function whose order is strictly less than n, okay, of smaller order. Okay, now here is two important results regarding this realization business. okay, which will connect the transfer function to the concepts of controllability and observability of the system. And by system I mean the state space system, system that's given by that state space representation. Okay, here is one. A realization is minimal if and only if it is both observable and controllable. Okay. And here is the second theorem, which says that all minimal realizations, okay, so given two minimal realizations of a given transfer function, okay, those two state space representations must be algebraically equivalent to one another. Okay, so all minimal realizations algebraically equivalent. Okay. Now let's also say a few things about the special but important case, namely the single input, single output case. Okay, SISO case. Now, when the system is single input, single output, meaning that this n and k, they're both 1. So that means we're talking about a scalar when we talk about the transfer function. And that means we can write the transfer function as simply a rational function, some numerator polynomial divided by some denominator polynomial. So let g of s be numerator polynomial divided by denominator polynomial. Okay, and suppose that GS is proper. Okay, that is, degree of numerator polynomial is not larger than the degree of denominator polynomial. Okay, and second condition that we want g of s to satisfy is that all the Poisson cancellations have been performed. That is, numerator polynomial and denominator polynomial are co-prime. Okay, that is, they do not share a common root. And the final condition that we require our g of s to satisfy is that the denominator polynomial, and it can always be put in that form to satisfy that condition, denominator polynomial is a monic polynomial. Okay, that is, the highest order term has coefficient 1 plus 1. Okay, so denominator polynomial reads as n plus a 1s to the n minus 1 and so on. Okay, so such polynomials are called monic polynomials. Now, this is the transfer function, and these are the conditions we're working under. And for this transfer function, suppose we have the following. Realization. Okay, so let x dot equals ax plus bu, y equals cx plus du, be a minimal realization of this g of s. X is in Rn, u is in R, and y is in R, because we're considering the single input, single output case, okay? K is 1 and m is 1. So let this be a minimal realization of GS. Okay, then here is an important relation between the denominator polynomial of the transfer function and this representation, or in particular the A matrix. We have the following: the characteristic polynomial of the A matrix, okay, determinant of Si minus A, equals the denominator polynomial, okay, of the transfer function g of s. And an implication of this is the following: consider a single input, single output system that's both controllable and observable. Okay, both controllable and observable. Now, this system is bounded input, bounded output, stable, if and only if, okay, it is also exponentially stable in the sense of Lyapunov, okay, in the sense of Lyapunov, okay. Now, we already talked about something similar to that, which was, given a system, we didn't use the adjective minimal in that setting. Given some state space representation and the transfer function corresponding to that. Now, we said this system, okay, is bound input, bound output stable if all the eigenvalues of A are with strictly negative real parts, okay? But that, we said, is just a sufficient condition, because there exist cases where the system is not exponentially stable in the sense of Lyapunov, and we still have bound input, bound output stability. But now, this result here, or this implication here, says that if the system, if a single input, single output system is both controllable and observable, then it's bound output stable if and only if, okay, it's exponentially stable. Therefore, we already had that exponential stability implies bound input, bound output stability, but under controllability and observability condition, bound input, bound output stability also this time implies the exponential stability of the system, okay. So under this condition, therefore, the implication became an equivalence.